for the afternoon session, and it's a pleasure to introduce Urs Lang this afternoon as our first speaker from ETH Zurich to speak on group actions on spaces with a distinguished geodesic structure.
Thank you. So I would like to thank the organizers for inviting me. It has been great. I'm sorry for my voice. I hope I'll be able to make it through the talk. Can you hear me?
Yes.
That's the micro. Okay. So some time ago, I got interested in spaces that are not uniquely geodesic, but still share a number of properties with cat-zero spaces. And so in the past few years, together with some of my students, we have worked out a number of things, and my talk will essentially be a survey on these results. So first, I should tell you about bicombings. So X is a metric space. Geodesic bicombing, or just a bicombing, for the purpose of this talk, is a map sigma from S cross X cross 0, 1 to X, so that sigma xy, which is sigma xy, so that's a map from 0, 1 into X. So that's supposed to be a geodesic from X to Y, right? So the map selects a geodesic for every pair of points, it selects a geodesic connecting the 2 points. And we will impose a convexity condition. So it's the following: D sigma xy t sigma x prime y prime t is less than or equal to 1 minus t times tx x prime plus t times dy y prime. So that's my definition of bicombing for the purpose of this talk. So that's a weak convexity condition. Of course, you have it for the geodesics in a cat-zero space or in a Busemann space. So these are uniquely geodesic spaces. So this condition holds for all pairs of geodesics. But here you only have it for a distinguished family of geodesics. Now, life is not that simple, so we have there are some more conditions we can impose on a bicombing. So we say that sigma is consistent if the following holds. So take one of these bicombing geodesics. So the image is a directed segment. Now take 2 points, P and Q, in that order. Then the bicombing geodesic from P to Q is supposed to be a subsegment. Right? So the image, in that situation, the image of sigma PQ is contained in the image of sigma XY. Consistent. Right? So if this holds, then in fact the function t goes to what we have here on the left-hand side, d sigma xy t x prime y prime t is convex. So maybe that's a bit confusing if you see it for the first time. Isn't that the convexity condition already? Well, it's not, right? Because this condition alone here only tells you that well, the graph of this function, if here we have the distance between x and x prime, and here the distance between y and y prime. So this condition alone only tells you that the graph of the function is below the line connecting the 2 points. So it need not be geodesic, right? But if you can pass this condition here to subsegments, then of course it follows that the function is convex, actually. But in order to pass it to subsegments, you need to know that the bicombing is consistent. So there are actually 3 different types of bicombings. There's the weakest form, this form here, and then there are, it might happen that the function is actually always convex, but the bicombing is not consistent. And the strongest version is if the bicombing is consistent, then it's convex. Okay, I'll write down the hierarchy later on. So here are some examples. Well, of course, as I said, everything holds for cat0 or Busemann spaces, and it also holds in norm spaces. Of course, there is a canonical bicombing, so if X is a norm space or a convex subset of a norm space, then sigma xy, well, if you just take the linear geodesics. And this gives a consistent bicombing. It's consistent. And a nice fact about bicombings in this weakest form is the following. They behave well under one Lipschitz retractions. So if you have, say, a bicombing sigma bar on x bar and one Lipschitz retraction from x bar to x, so onto some subspace, one Lipschitz retraction onto some subspace x, then you can simply, well, take the bicombing. So you take 2 points in x, connect the 2 points by the bicombing geodesic. Now you just retract the geodesic, and this gives a bicombing in x. So then sigma, which is rho. So we take sigma bar, the bicombing of the ambient space, but you restrict it to x cross 0, 1. This gives a bicombing on x. So that's another source of examples. So as a consequence of these two, you see that every absolute one Lipschitz retract has a bicombing. So an absolute one Lipschitz retract is just a metric space with the property that each time you embed it into isometrically into some metric space, and there exists a one Lipschitz retraction, right? And every metric space can be embedded into some Banach space. So, and in the Banach space you have the linear geodesics, then you have the one Lipschitz retraction. So this proves this fact. It's a combination of 1 and 2. Now, absolute one Lipschitz retracts are the same as injective metric spaces. And I will use this term. So what's an injective metric space? Well, it's called injective because it's an injective object in the category of metric spaces and one Lipschitz maps. So this means that whenever you have a one Lipschitz map into X and A defined on some subset of some metric space, say defined on A subset of B, then F extends to a map F bar from B. And the extension is again one Lipschitz. And it's easy to see that these conditions are equivalent, being an absolute one Lipschitz retract and being an injective metric space. So we know that every injective metric space has a bicombing. There is a stronger result. In fact, every injective metric space has an equivariant bicombing. So this means that for all isometries, if we map one of these geodesics by the isometry gamma, then of course we get the geodesic connecting gamma x and gamma y, right, for all isometries. So, well, this fact here, well, it's essentially the same proof as here, but there is just an equivariant version of this. It's implicit in a paper of Tres, and it's also in my paper. I worked it out from 2013. Maybe I should. And there are some more examples. So you might still wonder, well, are these conditions any different at all, right? But it's true. So there is an example of bicombing that is not convex. So we just have this weakest condition, but the function is not convex in general. So that's easy. You can use, well, you can produce it as a subset of R2 with the sup norm. You can do the following. I'll just briefly describe it. So take in R2 with the sup norm the following set square, a diagonal square, and attach some antennas. So say, let's say these points here are at the same height, height 1. So the solid square plus these two antennas. Now look at this triangle here. So that's a convex subset of R2 with the L infinity norm. And well, with respect to the L infinity norm, sup norm, well, this vertical retraction here is 1 Lipschitz. Now if you take the linear geodesic from here to here, some color. If you take the linear geodesic from here to here, after the retraction, the geodesic will look like this, right? And well, by 2, so you get a bicombing on this set. So the red geodesic is one of the bicombing geodesics. For the other one, you take the constant geodesic here. And then you see that the distance is 1 here, and 2 here, and 1 here again. So it's not convex. The function is not convex. So that's a silly example, but it exists. Somehow these examples are a bit artificial, but still it shows that the possibility is there. So, and there is an example of convex bicombing that is not consistent. So that's hard. So two students of mine worked it out, Giuliano Basso and Benjamin Miesch, in a paper on the archive last year. Well, the idea is similar as here, but it's much more delicate, and you have to make very, very tedious computations to check that all these functions are convex. Right? But it's not consistent. Okay, so that's now I can write down the hierarchy. I'll put this here. Hierarchy of global non-positive curvature conditions. So the strongest one is cat 0, so x is cat 0. The next one is Busemann, x is Busemann. And then the next one is x admits consistent bicombing. The next one is X has a convex bicombing. Oops. And the last one, E X has a bicombing. Oops. So if you look at Banach spaces, if X is a Banach space, then here we have exactly the Hilbert spaces. Here we have exactly the strictly convex, right? Strictly convex Banach spaces. And here we have all. So, Banach spaces. Okay. And as I told you, so, well, this class here, spaces that admit bicombings, is very rich. So here we have all injective metric spaces contained in that class. Okay. Now,
what's an injective metric space? Sorry.
the definition is here. So it's an injective object in the category of metric spaces with one Lipschitz maps as morphisms. So this means that whenever you have a one Lipschitz map defined on some set A into X, and A is a subset of B, then you can extend it to a one Lipschitz map on B. Okay. So basic examples of injective metric spaces are R, real line, all trees, all L infinity spaces. But I will just tell you that there are many, many more. Okay. So, yeah, in fact, so there are many, many more examples, because every metric space X has an injective hull. It's usually denoted EX. So there is a kind of smallest injective metric space containing an isometric copy of X. So that's an old construction due to Isbell, and he constructs it explicitly as a function, certain function space. He looks at certain one Lipschitz functions on X and takes the soup norm. So, and this has nice properties, nice functorial properties. So if you start with a finite metric space, then this gives a finite polyhedral complex with L infinity metrics on the cells. And if you start with a compact metric space, you get a compact injective hull. And so this gives a good source of examples for spaces with bicombings. So for example, if you take 2 points, then you just get a second connecting the 2 points. If you take a metric space with 3 points, then you get a tripod. So there is a unique tree, right, which gives correct length. And if you take a metric space with 4 points, then you get something like this. So you get some rectangle. If I draw it like this, it's with the L1 norm. Or if you put it diagonally in R2, then it's with the L infinity norm. And some antennas attached. So. And if you go to 5 points, then there are already, I think, three different combinatorial types. If you go to 6 points, there are over 300 different combinatorial types, and then it explodes somehow. But in any case, if you start with a finite metric space, you get a nice finite polyhedral complex. And the dimension of the complex is at most 1/2 the number of points in the space. Okay. Now, I would like to tell you something about improving bicombings. So a first observation, also by, it's in the same paper by Basso and Miesch, is that if X is complete, and sigma tilde, just a bicombing, so we are in class E, right? Then there exists a reversible bicombing. That's yet another condition. Reversible means that, well, sigma xyt is always the same as sigma yx 1 minus t, right? If you reverse the order of the points, then you get the same geodesic same segment, but parameterized in the other sense. So somehow reversibility is for free. You get it for free, and the proof goes like this. So you take 2 points. So here's the geodesic from x to y, and here's the geodesic from y to x. Right? Now you take the midpoints and take the geodesic from the two geodesics connecting the two midpoints. Looks like this. Now, from the bicombing condition, you can check that the length of these geodesics is at most 1/2 the length of the original geodesics. Now, if you iterate, then you get Cauchy sequences, and you get a canonical midpoint. So you get a symmetric midpoint assignment with the 2 points. And once you have this, you can produce the reversible bicombing. Okay. Now, so another result, which is in a paper with Dominic Descombes, another student from 15. If X is proper, with a bicombing sigma, so again we are in this class E, then there exists a convex bicombing. So this means that if X is proper, these two classes are actually the same. So I told you that there are some individual examples that are, well, examples of bicombings that are not convex, but if a space admits a bicombing, if the space is proper, you can produce a convex bicombing. Right? So for proper metric spaces, these two classes actually coincide, and we do not know whether the result is still true if we drop properness. So this would simplify things. And actually the same is true for these two classes here. So it's still conceivable that if a metric space has a bicombing, the most general type, it actually also has a consistent bicombing. And then all these classes would be the same, but we do not know how to prove it. So. But there is an improvement which goes from D to C. It's in the same paper. So there is some special assumption here. X has finite combinatorial dimension. So that's a notion that was introduced by Tres. The sense of Tres.
Could you just clarify what you said before? I thought you said it was still conceivable that E and C are the same, but doesn't the examples that you gave in 4 and 5 show that they're
well, that's for individual bicombings, right?
Ah, I see.
So there exists a bicombing that is not convex or not consistent, but it's still conceivable that if the space admits a bicombing, then you can produce a consistent one. Okay. So combinatorial dimension is the following. I told you that if you take finitely many a metric space consisting of finitely many points, then the injective hull is a finite dimensional complex, right? Now you just take finite subsets of X, and you take the soup of all these dimensions. So take the soup over all finite subspaces. So that's an extremely restrictive condition, but it's still good enough for an application. So that's a very strong condition. Finite combinatorial dimension. And so if sigma is a convex bicombing, then in fact we do not even need to change it. It's already consistent, so it's automatic. So then sigma is even unique. Under this assumption on the dimension. So it's the only convex bicombing on the space, so it's unique, and then it's also equivariant, it's also reversible and consistent. So you get everything you want in this case. So if you put the two results together, then this tells you that if you have a proper metric space with finite combinatorial dimension, if it admits a bicombing, then in fact it also has a consistent bicombing. So then we can go from E to C. Now in combination with a result I proved some time ago, this gives the following result. And so in combination with these two results, it follows that every hyperbolic group acts geometrically on a proper metric space with bicombing with these properties, with a consistent, reversible, equivariant, bicombing. So, well, for finite metric spaces, the injective hull is a nice finite polyhedral complex. But if you go to infinite metric spaces, then in general the injective hull is huge, right? But in that paper, I proved that for a hyperbolic group, you still get a nice locally finite, a nice proper locally finite polyhedral complex with finitely many isometry types of cells, and the group acts properly and co-compactly by isometries on the space. Everything is functorial, so the group acts on the injective hull. So when I proved this result here, it was already clear that, well, because injective metric spaces also have equivariant bicombings, well, we already knew that hyperbolic groups act on spaces of class E here, but now in combination with these two results, we know that we are actually here, right? So hyperbolic groups act on spaces of class C. And we would like to go up, right? So the next thing I would like to tell you about is Paris centers. So there is the following result. Well, that was in the literature for Busemann spaces, and exactly the same thing works for spaces with bicombings. So it's due to S. Sahib and Heimich from '99, and then Navas took it up and modified it a little bit, or simplified the proofs quite recently, and that's for Busemann spaces. But the same is true for bicombings. So X is complete, and sigma is a reversible bicombing. But as I told you, reversibility is for free, right? You get it once you have a bicombing, you also get a reversible one. So, and then for all n, there exists a barycenter map. There exists a map Bn from Xn. So you can associate a barycenter to every n tuple of points in X, so that well, the barycenter of x1 up to xn is in the closed sigma convex hull. Should be clear what I mean by sigma convex hull, right? We built the convex hull, but using the bicombing geodesics, the closed sigma convex hull of the points. And there's a very nice estimate on the distance. So if you take two such tuples, and note it like this: x underbar bn y. Well, this is less than or equal to 1 over n times the minimum. Minimum over all permutations pi in Sn, and then you sum. Well, here is dxi dxi y pi I. So you can permute the points, and then you sum up the distances, and you look for the best permutation, and you divide by n. So that's a very sharp estimate. And of course, if sigma is gamma equivariant for some isometry gamma, then gamma of Bn x is the same as Bn of gamma x. Right. So the idea of the construction is the following. So the bicombing is reversible, so we don't have to worry about directions. So if we start with 2 points, then the barycenter is of course the midpoint on the bicombing geodesic. Now if we take 3 points, then you just take the midpoints on all the sides. And then again, if you look at this new triangle here, then you see, well, by the bicombing condition, that it's at most half as big as the original triangle. And now you iterate. So you take again midpoints on the sides. It's a new triangle, and so on. And if you do this, then again you get Cauchy sequences, and this defines the barycenter of 3 points. Now, if you have 4 points, you go on like this. So if you have another point here, then you do the same construction on every facet. I mean, on the vertices corresponding to a facet. Right? And then, yeah, you go on like this. So that's a very beautiful construction, and this estimate here is optimal. So, and I think it still deserves to be better known. Now this can be extended to probability measures. So this construction can be extended to a barycenter map on probability measures. To a barycenter map on P1x. So these are probability measures with where there is some integrability condition, finite first moment. So this means that well, probability measures with well, you fix some base point and you integrate the distance function, and this should be finite. Does not depend on the base point. And well, from this estimate here, from condition from property 2, you get that this map here is 1 Lipschitz with respect to the so-called first Wasserstein distance. So d barycenter of mu, barycenter of another measure nu, is less than or equal to W1 of the two measures, 1 Wasserstein distance. So I'm not going to explain this, but for finitely many points, it's exactly what you have here. So that's actually the first Wasserstein distance of the corresponding probability measures. So you take 1 over n times the sum of the Dirac measures at these n points. Then this will be the first Wasserstein distance. So this plays an important role in optimal transport. And people are very much interested in finding such maps, barycenter maps. And the interesting thing is that, well, these are exactly the spaces with a bicombing. So the so-called barycentric metric spaces that admit the contracting barycenter map, are precisely complete metric spaces, are precisely the spaces of class E here. Because if you have such a map, there's a converse so if X is a metric space with a barycenter map from P1x to X, which is 1 Lipschitz with respect to W1, then you can write down a bicombing. Sigma xyt is just the barycenter of the linear, of the convex combination of the corresponding Dirac measures. And this defines a bicombing, reversible bicombing. So that's a nice fact, I believe. So the barycentric metric spaces are exactly the spaces of class E. So again, reversibility is for free, right? For complete metric spaces. Now, once you have a barycenter map, you get fixed point results. Right? So So that's the next topic I want to discuss. Fixed points. So here, the model result is, of course, the result for cat-zero spaces. If you have a group that acts isometrically on a cat-zero space with bounded orbits, then there is a fixed point for the action, right? Which has a very simple proof. And there is an analog of this for, maybe I will not write it down. Recently, Pater-Gelander Mono proved the analog for certain Banach spaces, in particular L1 spaces, for so-called L-embedded Banach spaces. And there is also a perfect analog of the result for cat-zero spaces for injective metric spaces. That's in my paper. So, but what about Busemann spaces? So is the result, the fixed point result for cat-zero spaces, still valid for Busemann spaces? Well, surprisingly, we couldn't find this in the literature. This doesn't seem to be recorded. We also asked some specialists, and they didn't know. And then turned out, well, the answer is no. So there is a counterexample. Maybe it was known to some experts, to some people, but we didn't find a reference. So there is now a reference in this paper by Giuliano Basso. There is a complete bounded Busemann space with a fixed point free isometry. And construction is actually not very complicated. So he starts with L1. L1 over the integers. So you look at all summable functions on the integers. And then, well, that's not strictly convex. So it's not the Busemann space. But what you do is, well, you use a standard result from functional analysis. You can switch to a strictly convex norm, which is equivalent to an equivalent strictly convex norm. It's a renorming technique, right? So you renorm it, and then you take the following. Well, you take the function that is 1 at 0. So take the indicator function of 0, and then you take the shift map that just moves this function along the axis, and you take the closed convex hull of this orbit. And this gives a bounded Busemann space which has no fixed point. So this shift map is an isometry. And the only fixed point is the 0 function. And in that paper, Giuliano Basso also has a positive result, so he proves that. Of course, I should say that, well, if you have a compact group acting on your space, then you can take the push forward. You take the Haar measure on the group, and then you take push forward under some orbit map. This gives an invariant probability measure, and then you take the barycenter of that, and this gives a fixed point. So if you have a compact group acting on the space, then with a bicombing, you just need a barycenter map, that's all. Then you get a fixed point. But there is a stronger result. It suffices to have a compact invariant set. And that's what he proves. So X is complete. So again, Giuliano Basso. X complete. Sigma reversible. Then we have the barycenter map and equivariant with respect to some group of isometries So if there is a compact gamma invariant set, then there is a fixed point. So on. The proof uses a result from functional analysis, one of the fixed point results. Functional analysis, well, actually to produce an invariant probability measure, and then he applies the barycenter construction. So there are some limits here, right? And that's the best we have at the moment regarding fixed points results. Now, next topic, isometries. Well, let's look at the usual classification of isometries, but now for spaces with bicombings. So, take a hyperbolic isometry. So this means that the translation length is positive. And the inf is attained, right? So if you have that, well, if you have an isometry with an axis, right, then this implies that the isometry is hyperbolic. So that's a general fact which holds in all metric spaces. It only uses the triangle inequality. But when is it true that hyperbolic in that, well, as defined here, implies that there is an axis? Well, what do you do? So for cat-zero spaces, you, well, take a point where the inf is attained, take the orbit, now connect the dots. Then you see that the midpoint of the first segment is mapped to the midpoint here, and the translation distance is well, so this distance here has to be at least the translation distance. So this shows that this curve here is a local geodesic, right? But then in the cat-zero space, a local geodesic is a geodesic, and the same works in Boseman spaces. So local geodesics in Boseman spaces are geodesics, but in spaces with bicombings, you cannot do that argument. But what you can do is, well, you just apply the barycenter construction. So you start here with x. So take the first n points. So here we have gamma n minus 1 x. So take this n tuple of points, and well, then the translation length is less than or equal to the distance. But well, this just uses the barycenter map for, as I stated it, for finitely many points. So take Bn of this n tuple denoted by x on the bar. So take the first n points here, and then you apply gamma again to the barycenter, right? So by definition, we have this inequality. Now here you can switch the order because it's equivariant. So this is the same as Bn of gamma x, and then you have the distance estimate. So that was property 2, less than or equal to 1 over n. Now, what do you have here? So gamma times x. So this moves every point to the next one, right? So you get essentially the same n points except for the first and the last one, right? So you match the points up in that way, so that the estimate just gives you the distance between x and xn, gamma nx. So here you have x, gamma n x, right? And this gives you just a sharp lower estimate on the distance of these points. So this shows that it's a geodesic, right? So this actually gives an axis. So for spaces with bicombings, where we have the barycenter map, we also have this implication here. So as in the case of cat-zero spaces or Busemann spaces. Now, okay. So you could also ask, well, so this gives an axis. It's a geodesic, but is it the sigma geodesic? So is it a sigma line, which would mean that it's compatible with the bicombing? If you take 2 points on the line, is the subsegment, well, is the bicombing geodesic actually a subsegment of the line? So do you get a sigma axis? The answer is no, in general. That's bad. But we have the following. So now we'll talk about flat subspaces and about a version of the flat torus theorem, which was mentioned yesterday. So flat subspaces. First of all, there's a flat strip. That's also in a paper with Dominic Descombes from last year. So if well, X has a consistent bicombing, now we are in class C, sigma consistent bicombing, and we have 2 parallel sigma lines, psi prime, 2 parallel sigma lines. So by sigma line, I mean a geodesic line that is consistent with the bicombing, right? So so they are at finite distance. Now you can do the following. So here is say psi of 0. Now take any real number a and look at psi prime a. Now connect the 2 points by the bicombing geodesic. Now slide it along the 2 lines. Then it turns out that, well, these segments will trace out a flat strip. So it's isometric to a strip in a normed plane. You get an isometrically embedded normed strip. If you change the parameter a, so if you do this for another slope, you might get a different strip. So for cat-zero space, you have, of course, uniqueness. The flat strip is the convex hull of the 2 lines. But here, uniqueness is lost, right? So you might get different flat strips. And the sigma convex hull of the 2 lines might be thick. So and we have explicit examples where you can show that this actually happens. So you still get existence of flat strips, but not uniqueness. And here's the flat torus. Theorem X proper sigma consistent and gamma equivariant, and gamma is a group acting geometrically. Then the following holds. First, well, I told you that in general it's not true that every hyperbolic isometry has a sigma axis. Unfortunately, that is not true in general. But here it's true. For the element of that group, it's true. So it's true that every gamma has either a fixed point or a sigma axis. Or a sigma axis. So the action is by sigma semi-simple isometries, if you want. Right? And the second statement is the flat torus theorem. So if there's a free abelian subgroup of rank n in gamma, then X contains a normed flat n-plane on which gamma acts by translation.
Probably means Z to the n.
Sorry?
Z to the n.
Oh, yeah, of course. Thanks. So that's the result. Now my time is almost up. So again here, well, I should also say mention some names here. Well, this flat torus theorem was proven by Bowditch for Busemann spaces in '95. And the proof here is actually much more complicated. So, so the idea is, well, first you show that the min set of z to the n is non-empty, and then you take, then you can produce the norm. So you take a point in the min set, and you take an orbit under this action of z to the n, and then you can already construct the norm from this. So you get an isometrically embedded copy of z to the n with some norm, and then you use the barycenter construction to fill the gaps and to complete it to a flat. So it uses again the barycenter construction, but it's involved. And it's not true in general that the that this normed flat is sigma convex. So it might be quite strangely folded in the space. Right? And if you take 2 points, then somehow the bicombing geodesic will not stay in the flat in general. So again, uniqueness is lost, but some properties are retained. There are some more results. So Dominic Descombes has another paper with quite strong results. Among other things, he proves, well, he proves this characterization of Gromov hyperbolic spaces. If you have a proper Gromov a proper metric space with a bicombing, so he just needs the barycenter construction, then it's hyperbolic if and only if it does not contain an isometrically embedded normed plane. So again, well, this was stated by Gromov in his paper on hyperbolic groups, and then Bryson gave a detailed proof of this, and then Bowditch gave a proof for Busemann spaces, and now Dominic Descombes has a proof for the most general class of bicombings. We had also more explicit proof for consistent bicombings, but he has now a better result for general bicombings. Okay, so I'll stop here. It would be nice if someone could make progress on these questions here. I would love to know that all these classes are the same. This would actually simplify. This would simplify things, right? So, thank you very much.
Are there any questions? We've got time for a quick question.
I'm not sure if this is a quick question, but I mean, you just told us that, you know, we've got a hyperbolic, you know, if I've got a hyperbolic group, you can find, you know, a nice consistent a space with a nice consistent bicombing, and you've just proved most of my favorite theorems that I would have if I knew it was cat zero. should we actually care anymore whether hyperbolic groups are cat zero, or should we just be happy with consistent bicombing?
I would be happy if you would be happy with that.
Maybe you should try to persuade us, and then we can.
So I'm still working. Well, maybe it's not the right question to ask. Right? I'm not sure anymore. I had some discussion with Damian Osaida about this, but I'm still working on this a little bit. I'm trying to put the cat zero metric on the injective hull, and I have some partial results, but I cannot prove the full result at the moment. So.
Thank you. Now we better press on. Let's say thank you to all of us today.